Today we're going to come up with a handy change of base rule. And this is necessary, well, number one, you know that when you go to use your calculator and you type in that log function and it presents you with that little box, but you can't use it. It's just a big tease that it's there, but there's nothing you can do to use it. It won't let you change it. So if we were not in press to test mode, we could put a 2 in here, we could put an 8 in here, life would be good, we'd get the answer, and it would be a one-step deal for us. But we're not allowed to use that. So we're going to have to learn how to use this change of base rule, which is not hard. It's actually very easy to use. Before I show you the change of base rule, let's watch what happens if we take this exponential expression and we turn it into exponent form. So we're going back and forth using log by, which means my base is equal to 2. My exponent's coming from the end and the argument is the answer. So I'll turn this around into 2 to the x is equal to 8. You probably can guess at this point that x is going to be equal to 3. But instead of solving it, let's just take the log of both sides, as we did in our application problems yesterday. And after we take the log of both sides, we'll swoosh this exponent down to be a coefficient in front. So now it's x log of 2 equals log of 8. And the last thing we're going to do is we're going to divide both sides here by log of 2. And after I do that, I end up with x equals the log of 8 over the log of 2. Now let's talk about that for just a second here. We are going to assume we have bases of 10 on both of these. These are both common logs. We don't see the base, so they're both base 10 logs. And now we know we could pick up the calculator. We could type in log of 8. It would put the base of 10 in there for us. We'd type in log of 2 on the bottom of the fraction. We'd put the base in for us, and we would get an answer from our calculator of 3. So if we could use that little base, we'd get the 3. We can't use the base, no big deal. We'll just change them both to base 10 logs because that's what the calculator let us do, and we'll change to and our answer will be 3. Okay, so this change of base rule, it is easy, and promise easy. Here it is. We start out with log base 2 of 8. And we finish up with it being the equivalent of log 8 over log 2, both of them common logs. So what we're going to do is we're going to be able to go directly from the top to the bottom and skip all the middle steps. And the easiest thing to remember here is that this little base here, the base goes on the bottom. So we're turning this into a fraction. It's going to be a common log on top. It's going to be a common log on the bottom. And it's the base. Can't use these parentheses. It's the base. I'm going to erase that and try something else. I'll use the pen. Okay, so it's the base of 2 that's going to go on the bottom of the fraction. And it's a very simple thing to use. It'll allow you to quickly evaluate any log that has a base other than 10. And it's also going to allow you to quickly graph now any log function. At the beginning of the unit, you saw me graph an exponential, and then I graphed on the same graph. I had the log graphed, and I was actually using my software, which is not in press to test, so I can actually type this in directly and ask it to graph for me. But you can use yours in press to test by taking that log base 4 of x and turning it into log of x over log of 4. Base 10 logs. So you see that was done right here in blue. I used log of x over log of 4. The calculator filled in the tens for me, and it drew this blue curve right here. Okay, well, while we're looking at a graph, let's just talk about a couple of other things on this graph. I've got 3 logarithmic functions here. The blue one started off as log base 4 of x. The red one started off as log base 10 of x, just a common log. And the green one started off as log base 2 of x. Well, I think you can see from this picture that we have not a horizontal asymptote anymore, but now we have a vertical asymptote. Remember, in our exponential functions, we had horizontal asymptotes on the x-axis. Now, with the inverse function, we've got vertical asymptotes on the y-axis. Everything is kind of turned around because of that whole inverse idea. We don't have any horizontal asymptotes here. I think it might be more obvious to you that this thing is still going up at a pretty good clip, but eventually you're going to stop seeing that good clip. You're going to see something that looks more like this. Eventually it's going to look more like it's leveling out. But you don't have an asymptote here. This thing will keep going up. It's going to go up slower and slower and slower, but it does keep going up. This one looks like it's almost leveled out already, but in fact it is just growing at a slower rate, so it's going to go up a whole lot slower than the blue one, and the blue one is a whole lot slower than the green one. By the time you get out to, well, we're looking at 200 here. By the time we're out at 50,000, all three of them are going to look pretty flat because your eye can't tell the difference, but they will still be going up. Okay, so what happens if I ask you to graph a log function? Well, first of all, you can't graph it this way with your calculator. We'll turn it into something your calculator will understand, which would be f of x is equal to log of x over log of 2, and you know by now when you type it, it's going to fill in. We're giving you grids tonight to graph some of these with no quadrant 2 and no quadrant 3, and that's because we know that exponential functions can't have negative x's as inputs to the argument. You'll get an error there. The functions only exist in quadrant 1 and quadrant 4, just like your exponentials, unless we've transformed them, only exist in quadrant 1 and quadrant 2. So we would begin by putting this into the calculator. Our job when we're looking at the calculator, again, I want you to spend more time looking at the function in the calculator before you start plotting things on the graph. You want to plan out your graphs, and you do that by asking the software to show you what the function behavior looks like. So we're not given any domain here, so we'll have to choose an appropriate domain in order to come up with our XY table. We do have an asymptote, but the equation of the asymptote for any of these logarithmic functions, unless we've transformed them, is going to be it's going to be x is equal to 0. That's the equation of the asymptote, because x is equal to 0 is the equation of the y-axis. If we want to accomplish a vertical shift or a horizontal shift, things aren't dramatically different than they were for any other function. If we want a vertical shift, in other words, we want to move it up or down on the graph, we can add some number at the end that would shift the whole thing up. We can subtract some number at the end that would shift the whole thing down, and we call those vertical shifts. Horizontal shifts are numbers that occur inside with the x. So if I wanted a horizontal shift, and again it's kind of opposite signs, log base 2 of x plus 3 would be shifting that whole function to the left 3 units. A log base 2 of x minus 5 would be shifting the whole thing to the right 5 units. And again, the calculator is the best. It's your go-to to determine what happens when you're shifting these things around. So let's just look quickly at a picture of log base 2 of x in your calculator. And you'll have to type it as, I'm going to use my log button here. You'll have to type it as log 10 over log x over log 2. They'll say the same thing. As a matter of fact, I'll show you. If I do go back to Control G and instead I type it in using my change of base formula, log of x on top and log of 2 on the bottom. Base goes on the bottom, and you'll see that that orange thing that I typed in is now right smack on top of the green one. Okay, so there's our function. Obviously it doesn't exist in quadrant 2 and quadrant 3, so we have no need to plot that on our graph. I'm going to leave this at -1 just so you can still see that y-axis clearly. And now we're going to pick some appropriate points. Well, you'll watch this and the graph isn't going to change much. I'm going from 0 to 10 here, but heck, let's go from 0 to 100 and see what happens. Not too much. I'm still not seeing anything very interesting or unique or different out here. If I go to 1,000, what happens? If I go out to 1,000, now it just becomes more difficult to read. So we want to choose something appropriate. Let me go back to 10 and let me peek at the table and see what the table is kind of showing to me here. If I go to Control T, well, I want to grab those integers. I really don't want you spending your time writing all those decimal numbers. Remember that green and orange are the same function, so let's just look down the green column here. 1, 0, 2, 1, 4, 2, 8, 3, 16, 4, and you know what? By the time you get down to 32, 5, you've done plenty of scrolling. So if you're going to go out to 32, you're only going up as high as 5 on the y-axis. So when you look at your grids tonight and you see that your grid looks more like this, it's because your your y-axis numbers are going slowly, but you're moving a lot faster out on the x-axis. So grab something reasonable, put it in your table. Please be sure you're making tables for all of these. And if you do have a transformation, graph it first. You'll see what's happening to it, and you can graph from there. You'll also have a number of application problems. We'll try some more of those tonight. This time, again, graphing or solving algebraically instead of graphically. Less work to solve them algebraically.